Thanks a lot, everybody, for coming. This is actually my first talk at a JuliaCon, so I'm very happy with it. Hopefully not the last one, since Eindhoven is close to home. So today I want to talk to you about Julia Smooth Optimizers, but I first going to talk about myself. So I'm a Brazilian. I have been a Brazilian my whole life. I was a professor in Brazil from 2014 up to 2 years ago. I then moved to the Netherlands to be a research software engineer at the Netherlands East Science Center. And when I was a professor, I used Julia for everything. I was looking for a new language, essentially. Somebody introduced me to Julia, which is the normal way to learn about Julia. And I used Julia for my research, which became Julia Smooth Optimizers, for classes and all of those stuff. And so when COVID hit, I put all my classes online, and that essentially made me a Julia YouTuber. My classes were in Julia. Just 2 videos, example that I have. I have this first one, which is a mathematical model. It's an interesting example with the mathematical description and implementation in Jump. And I have this other one, which is kind of a clickbait kind of video. You can guess which of these got more attention. Please check my channel, Abel Siqueira, like and subscribe. And I also want to talk a bit about my employer, so the Netherlands East Science Center. We are about 80 research software engineers, and the way that the Netherlands East Science Center works is we receive money from the government, so we are a kind of not-for-profit organization, and we open calls for researchers in the whole Netherlands. So any researcher can apply for us, for our calls. And instead of giving them money, we work with them. So research software engineers are assigned to the project, and we try to help in various ways. For instance, increasing accessibility, as you saw today, but also creating new software, if that's the case. We have a variety of fields that we work in. And a personal example, we work in various kinds of projects, so I don't use exclusively Julia. Actually, I only use Julia right now in the current project. I have used JavaScript, Kubernetes, and a bunch of other things in my current position. It's a fun project. If you're interested in this kind of field, we also have vacancies with some frequency. Okay, so Julia Smooth Optimizers. First, where is Julia Smooth Optimizers? You can find information about us at jso.dev. I will be using JSO a lot, Julia Smooth Optimizers. Also, we are Julia Smooth Optimizers on GitHub, and you can find us on common channels from Julia, the Slack, Zulip, and wherever else. The second question, who is Julia Smooth Optimizers? So the main core of Julia has been developed by me and the Professor Dominique Corbin for a long time, as Dimitri said. We also have 2 other core developers, Tanguy and Alexis. They are doing a lot of work in the main, the central part of that supports everything that Julia Smooth Optimizers does. And we have a bunch of other contributors, many students from me and Dominique, and a lot of people from outside or direct teaching involvement. And of course, if you want to get involved, you're most welcome. And finally, why is Julia Smooth Optimizers? The basic idea of why we created JSO in the first place was to empower research in nonlinear, non-convex numerical optimization, which is a nice way to saying that we wanted to have the code because our research needs the code. It's us. We are the researchers that need JSO. But of course, we try to do it in a way that helps other people. And it started with Qtest. So this is an optimization package for doing benchmark. It's a Fortran package. I had to use it in my PhD. And so a large chunk of my PhD was helping people install and use Qtest because it's hard. Ranieri Gaia Silva, which is a colleague, a shout out to him. He started a port to Julia. So this was during my PhD, so I was most not focused on that. It did not work. I helped a little bit trying to make the Fortran installation. And so in 2015, when I actually had the time, I started again. And this time, Dominique Corbin was also doing the same thing. He's one of the developers of Qtest, and because of that, we joined forces to have Qtest.jl, which is the first package that enables researchers in the nonlinear optimization to use Julia in a larger scale. So now we have over 50 registered packages. As just to give an idea, I give you here the graph of how it's structured. In short, it's kind of a mess. The black packages, these are all packages, registered packages. So the black ones are external packages, and the others are color-coded in a way that doesn't matter right now. And we have a collective over 1,000 stars, which is actually not a lot. So you can also start a few of our packages if you have the time. Okay, so serious business. What have we been doing for 8 years? First thing, we have been doing research and optimization and linear algebra. I'm not a researcher anymore, research software engineer, officially not a researcher, so I don't do that, but Dominique Corbin still has students doing papers and other things like that. Second, we have been working on streamlining solver development, which is kind of a way of supporting the research in nonlinear optimization. And we are also working on user-facing packages. A few you might know already, and a few are kind of new. So just to say that we have been doing research, this is a list of 21 research papers that we have related or using JSO, and you don't have to look at them. Let's look at more fun stuff. So this part of the talk is kind of dedicated to people that know a bit more about optimization. If you're doing a PhD or a master's and you want to work with optimization, you want to develop optimization solvers, this is kind of for you. So I will try not to be long here. The main idea of JSO solver development is this box, which is what we are calling a JSO compliant solver. As a researcher, you want to focus on the new solver part. You have an idea. You have some math that say, okay, this is new. It looks like it can work. Prototype that, right? So you just want to quickly prototype something. We provide the structure, so you don't have to worry about the input and the output. You just worry about the math part of it. So there are many implementations of NLP model, right? The abstract NLP model is defined somewhere, and there are many implementations. Some are very easy to use. Some are research only people that actually need to put it in the paper will do that. Some are like using a modeling language like JUMP or Ample, and some are some cool stuff like the PDE NLP model, which is if you want to use grid app to define PDE, partial differential equation, and use that as a constraint for your optimization solver, well, you can create that as well. So if you follow this structure for your solver, you can quickly prototype something. So you have a basic idea. You do some very basic linear algebra in your prototype, just backslash, and use dense matrices. And you can use ADNLP model, which is one of our user-facing packages. The main back end of ADNLP models is forward diff. So you might know forward diff. It's like one line automatic differentiation, but not very efficient for large scale. And when you're ready to move to like really research-ready solvers, you want to use like large-scale linear algebra. So for that, we also have some packages. We have things for sparse coordinates, so sparse matrices in general, factorization packages and wrappers. And we also have tools for matrix-free linear algebra, which is kind of what we like a lot. So this package Krylov.jl that you might know that implements some iterative solvers, and linear operators, which is a lazy matrix that you don't implement the matrix explicitly. And the idea being that now that you have your solver, you get another solver, you get a collection of problems, all the red things on the top, and you just run all of those things very easily to get a table, a LaTeX table that you can just put in the back of your paper, and one of these cool graphs that we nerds call a performance profile that I have to always explain that is not that kind of performance profile. It's a very specific one that nobody else cares about. But it's super important for the paper. Finally, some more general audience kind of packages, the user-facing packages that we have. So we have, first and foremost, Krylov. Krylov is, like I said before, is a package with iterative solvers. The Krylov methods, more specifically, and so if you don't know what Krylov methods are, you might have heard of conjugate gradients. So conjugate gradients, they do some kind of subspace minimization that is very efficient and doesn't require the full matrix. It only requires a product of a matrix and a vector. And there are a bunch of methods, actually, that you can do following that idea. That's the basics of Krylov methods. There are a bunch of Krylov methods. There are new Krylov methods coming out. And actually, I think 5 of the papers that I showed you are new Krylov methods that are implemented in Krylov.jl. And for people that, like us, that just want to use something to solve, I just want to use CG or MinRes or GMRes, LSMR, some of those most traditional Krylov methods, those are, of course, implemented as well. I dare say very efficiently, and I can say that because I'm not implementing them. I can just point to the students that are. So on the left here, we have a basic usage of Krylov. So you're creating a matrix. This is a dense matrix, n by n matrix. I won't look at the size. And you can just call Krylov.cg AB. So this is the equivalent of A\B for a dense matrix. This one needs to be a positive, definite matrix. And on the right, you have the preferred way of using when you're dealing with large scale, which is you don't have the explicit matrix, so you don't create the memory for the matrix. You have a function that gives you the result of the multiplication of the matrix times a vector. So here the res, the result, is A times V, and the result is computed this way. You don't know the matrix, you don't need to know, but, well, somebody has to implement it correctly. This function is passed to a linear operator, which is our choice of an object that is lazy, but you can use other things as well. And then you can just say CG of AB like you had previously, right? So it's efficient for large-scale problems, and it doesn't allocate, and it works with GPU, it works multiple precision. It's like a really important package. And this is probably our most used package. We have 21 direct dependencies and over 300 indirect dependencies. And many of those are, of course, IML, because they have 100 packages in those indirect ones, maybe. But still, a lot of packages that are not SciML are using our stuff, which is great. The other user-facing package that I have, we have is ADNLP models. And the basic idea is you just give a function here, and you say, this is the function that I want to minimize. You have a starting point. This is a traditional optimization problem. So minus 1.2 and 1.0, this is a Rosenbrock function. And then you just get the derivatives automatically using, in this case, forward diff. When you call has right here, you're computing the Hessian matrix. This is a dense matrix. When you call grad here, you're computing the gradient. So has / grad is Newton method. So this is an implementation of a Newton method, like a class worthy implementation. Just, hey, students, this is the Newton method, right? So it just works. You can do something similar for your prototype. If you want to do something a bit more convoluted, for instance, you have a 5,000 variable problem, you don't want to use a dense matrix, you can change the back end to something else. So for instance, here we are using symbolics. And with symbolics, you change the Hessian back end. You have to be explicit here. And the has that I have in the same Newton method is now a sparse matrix. So has / grad, still a Newton method, but now Julia is dealing with the sparsity and the linear system. And also, if you don't want to use the matrix at all, or you don't want to use symbolics, or if you just like matrix-free linear algebra, as we do, you can, for instance, call has up, has op does a wrapper around a function that computes the product of a Hessian matrix and a vector. So that gives you the result of Hessian times V, which means that you can give it to Krylov. So you can say this is a linear system with the Hessian wink and a gradient, right? So it's a wrapper, a linear operator one that does the fun stuff for you. And this is, again, a 5,000 variable problem. It does not compute the matrix, right? So even though it uses forward diff, it's not computing the matrix. Our other user-facing packages are optimization packages. Hopefully we have a few of those as well. So our solvers, the main ones, we have about 8 solvers, I think, but the main ones are JSOSuite. JSOSuite includes LBF.js and trunk, which are an LBF.js method, line search kind of method, and a truss region Newton method. So you have the two most commonly desired unconstrained problems, methods for constrained problems. And you have tron, which is a bound constraint method, is an active set, is not interior point, which is another liked method in the field. And you have, on the other end, Percival.jl, which is an augmented Lagrangian second-order method based on a paper by Dominique Urbain and implemented by one of my students, Egmara Antunes. Percival, I dare say again, is a very nice solver. It works well. It's pure Julia, so it's a nice alternative to some of the other, like really, really better solvers, I would say, like IPOpt and Nitro. They are many years old, many developers involved in that. But Percival is a pure Julia alternative that works really well. And one easy way to use Percival is just to call Percival. That's it. You create an NLP problem, you call Percival, and you get the output. Right? So this just solves the problem. There are also, how do you say, more efficient ways to use Percival if you really, I want to pre-allocate the memory that I'm going to use inside Percival and etc. Sure, you can use in another way. There are things that you can create. But like, again, focusing on the more user-friendly things, just call Percival and you get the solution. Here I have one cool thing about Percival, and this is kind of a late addition. If you have, Percival is a second order method, so some people were asking like, oh, I actually want to use a method like Percival, but I don't want to compute the Hessian. Can I use the BF.js matrix? And we actually had a thing for that ready, which is this LBF.js model of an NLP. This is tricking the optimization problem, tricking actually the Percival into, when you ask for the Hessian, it instead gives it a LBF.js approximation. And this works because Percival is matrix-free. So it never actually asks for the full matrix, it just asks for a product of a matrix and a vector. So you can do that with a limited memory BF.js, and that's pretty cool. So Percival is nice, so people are actually using it. You might already have used it. Percival is being wrapped by nonconvex.jl. The colors here are not actually really different, but these 3 packages are in a different color because they are external packages. The other ones are our things. Percival is being wrapped by nonconvex.jl. That is being wrapped by optimization.jl, which is what SciML maintains, right? So Percival is actually already available for use. So you might have been using it if you're using optimization. But there are other ways to use it as well. One of the ways that we like is using NLP models jump. So NLP models jump is a kind of a bridge between the jump modeling language and our NLP models. So you can create NLP models by giving it a jump model problem, or you can, now, a recent addition by Benoit Legat, you can take one of our solvers and give it to jump, and jump does its thing. So you don't have to really worry a lot about what we do about our API if you just want to use Percival. And finally, one new addition is JSOSuite. It's a kind of a newer thing. JSOSuite is our version of a user-friendly package that deals with optimization. Let's get there soon enough. So just to show you the differences, so here in the left, you have just a normal jump problem. But in the beginning, we are saying that the optimizer is NLP models jump.optimizer, and the solver is JSOSuite.lbfjs solver. So you can use our LBFJS with jump right now. And the other way to use it is through our way, which is you just create a jump problem without a solver, and you convert it using math-op NLP model, which is a mouthful, and then you just call LBFJS, and that works. Okay? Oh yeah, and this is a nice plot about the problem that they are solving. I just want to add some more figures. I think he lagged a bit on the figure side. So, user-facing packages number. Oh yeah. So before I move on, this is also some new thing that you can do. So you can mix and match. So you have jump. You can solve the problem with jump. It can be our solver or not. And then after you have that, you can also convert the problem into our NLP models and do other stuff like getting the hashing. So it might be easier to just call our NLP models and get the hashing than it is with a math opt interface. But that's more of a opinion kind of way. And finally, we have JSOSuite, which is our newest package. JSOSuite is trying to essentially hide what's going on behind the scenes, so you don't have to worry about the details. So the basic usage is you just give a lot of functions, objective function, constraints, bounds, and you just say starting point, and it solves what you're doing. Minimizes the function. You can override this and say, I actually want to use specifically the Percival solver, or you can just give it the function and it finds you a solver. Depends on your problem, so if you give it a constraint problem, it will probably use Percival. If it's unconstrained, it will use LBFJS and so on. And one cool thing, of course, that you can do with a lot of our solvers is callbacks. Everybody loves callbacks. Callbacks are very nice. And this is a simple example. This is a callback function with a lot of plotting in between that I hid. And this is how you call the problem, just the function, starting point, some tolerances, and the callback, right? So it just works. And I have the callback logistic if, which is this. So it's a logistic regression for a classification problem. And this is how the LBFJS changes over iterations, okay? All the solvers that I mentioned today, they accept this callback. This is the syntax. This might be one of the things that we use for as a definition of JSO compliant solver. But yeah. And finally, to finish, I just wanted to reiterate, we are at jso.dev. You can find a lot of tutorials there, more general tutorials. You can find some news, and you can find our communication channels. If you want to get involved or know more, just contact us in any of those channels. And you can always complain about a missing tutorial. And thanks a lot, and please.
Thanks, Abel. It was a great talk. Does someone have a question? Okay, while people are thinking, I have a question for myself. So you have a big ecosystem. How do you manage to maintain it?
Yeah, well, how do we maintain that? Essentially, we struggle a lot with a lot of our cutting-edge packages. Like many of our students are working on the fringe of that graph, right? So we sometimes miss a bit of what's going on. So we try a few of the more traditional Julia packages like compat helper. We do some kind of upstream dependency or downstream dependency checking. And recently we have been dabbling on a template that I'm working on, something called copier template, that hopefully will solve a lot of the smaller problems, like if you just change one version and you want to change 50 packages. Because currently what we do is, okay, we have to change the latest stable on the CI. So I do a mass GitHub action to change all at the same time, and then you have 50 pull requests that then I have to go also check that they're working. So yeah, essentially we have a lot of difficulties with maintaining that.
Yeah, I can imagine. Does someone else have a question there?
You talked about forward diff at some points. Is it possible to switch this auto diff backend?
Yeah. So forward diff is used because it's super nice, right? I believe you have by default maybe forward diff and reverse diff. And I think we have symbolics if you add symbolics and possibly something else. It is possible to change very easily a few of the functions, like you can easily create a new model and you implement it yourself. But if you want to really like, oh, there's something new going on, then you have to implement some of the harder functions, which takes a long time. We were looking for people maybe interested in integrating abstract differentiation, I think it's called, right? I haven't found anyone yet, but yeah. Thank you.
More questions? Okay, we still have room for questions, and I will ask more questions. So you work in eScience Center, and maybe you can share some sort of an example of a collaboration maybe with industry, like who actually use Julia Smooth Optimizer's ecosystem.
Great. So actually, I can say that nobody's using Julia Smooth Optimizers there, which is a pity. Something that I have been looking for some time. No one is using our packages directly at eScience Center, except maybe Krylov, but that's maybe in a few months. We have collaborations with industry in some other Julia and in various fields. In particular, I am working on an energy model problem with TNO. We are using JUMP there. We have another project that might be using the SciML ecosystem. And we have another project that was, I don't know if I can say this actually. We have a project that might be approved or not that is related to differential equations. That's, yeah. It's not public yet, I have to remember that.
What is your favorite solver, why, and how does it work?
Good question, good question. I think my favorite solver would be, I think LBFGS is my favorite one, because it's like very simple to explain, well, for a mathematician, it's kind of simple to explain what's going on, and it's like really efficient for very large scale problems. So it's like, it's the most used solver in data science. So it's the favorite.
And if it's easy to explain, can you briefly explain?
No, just, well, maybe the basic idea is that instead of using the full matrix, you start with a gradient method, which is super easy. Everybody uses gradient when they start. And they say, what if we change the matrix to be a little bit closer to the current curvature of where I'm standing? And then you do a bit of a kick that is cheap, and then you just improve over time. So if you're in a quadratic space, eventually you will be fully equal the quadratic space, which is nice because locally you can approximate things by quadratics, and that's the short version of it.
Cool, thanks.
Thank you.
Okay, I think we have time for one more question, maybe, yes?
What is large scale? Yes. Large scale is kind of ill-defined because we also don't have a good example. So for us, I think the largest problems that we are dealing with at Qtest, I think is on the order of hundreds of thousands of variables. I think we might have a few that are larger, like the bundle adjustment problems, might be a bit larger, a few million variables. Yeah, but like we abstain from actually defining because it's problem dependent, so more on the application side.
Okay, thank you again. We were happy to have you here today. Extra round of applause.